In statistical hypothesis testing, a type 1 error is the incorrect rejection of a true null hypothesis, while a type 2 error is the failure to reject a false null hypothesis. More simply stated, a type 1 error is detecting an effect that is not present, while a type 2 error is failing to detect an effect that is present. The terms type 1 error and type 2 error are often used interchangeably with the general notion of false positives and false negatives in binary classification, such as medical testing, but narrowly speaking refer specifically to statistical hypothesis testing in the Neyman-Pearson framework, as discussed in this article. Definition: in statistics, a null hypothesis is a statement that one seeks to nullify with evidence to the contrary. Most commonly it is a statement that the phenomenon being studied produces no effect or makes no difference. An example of a null hypothesis is the statement, "This diet has no effect on people's weight." Usually an experimenter frames a null hypothesis with the intent of rejecting it. That is, intending to run an experiment which produces data that shows that the phenomenon under study does make a difference. In some cases there is a specific alternative hypothesis that is opposed to the null hypothesis. In other cases the alternative hypothesis is not explicitly stated, or is simply, the null hypothesis is false. In either event, this is a binary judgment, but the interpretation differs and is a matter of significant dispute in statistics. A type 1 error is the incorrect rejection of a true null hypothesis. Usually a type 1 error leads one to conclude that a supposed effect or relationship exists when in fact it doesn't. Examples of type 1 errors include a test that shows a patient to have a disease when in fact the patient does not have the disease. A fire alarm going off indicating a fire when in fact there is no fire, or an experiment indicating that a medical treatment should cure a disease when in fact it does not. A type 2 error is the failure to reject a false null hypothesis. Examples of type 2 errors would be a blood test failing to detect the disease it was designed to detect in a patient who really has the disease, a fire breaking out and the fire alarm does not ring, or a clinical trial of a medical treatment failing to show that the treatment works when really it does. In terms of false positives and false negatives, a positive result corresponds to rejecting the null hypothesis, while a negative result corresponds to failing to reject the null hypothesis. Roughly, positive equals alternative, negative equals null, or in some cases, positive equals null, negative equals alternative, depending on the situation and requirements, though exact interpretation differs. In these terms, a type 1 error is a false positive, and a type 2 error is a false negative. When comparing two means, concluding the means were different when in reality they were not different would be a type 1 error. Concluding the means were not different when in reality they were different would be a type 2 error. Various extensions have been suggested as type 3 errors, though none have wide use. All statistical hypothesis tests have a probability of making type 1 and type 2 errors. For example, all blood tests for a disease will falsely detect the disease in some proportion of people who don't have it, and will fail to detect the disease in some proportion of people who do have it. A test's probability of making a type 1 error is denoted by alpha. A test's probability of making a type 2 error is denoted by beta. These error rates are traded off against each other. For any given sample set, the effort to reduce one type of error generally results in increasing the other type of error. For a given test, the only way to reduce both error rates is to increase the sample size, and this may not be feasible. These terms are also used in a more general way by social scientists and others to refer to flaws in reasoning. This article is specifically devoted to the statistical meanings of those terms and the technical issues of the statistical errors that those terms describe. Statistical test theory. In statistical test theory, the notion of statistical error is an integral part of hypothesis testing. The test requires an unambiguous statement of a null hypothesis, which usually corresponds to a default state of nature. For example, this person is healthy, this accused is not guilty, or this product is not broken. An alternative hypothesis is the negation of null hypothesis. For example, this person is not healthy, this accused is guilty, or this product is broken. The result of the test may be negative relative to null hypothesis or positive. If the result of the test corresponds with reality, then a correct decision has been made. However, if the result of the test does not correspond with reality, then an error has occurred. Due to the statistical nature of a test, the result is never, except in very rare cases, free of error. Two types of error are distinguished: Type 1 error and Type 2 error. Type 1 error. A Type 1 error, also known as an error of the first kind, occurs when the null hypothesis is true, but is rejected. It is asserting something that is absent, a false hit. A Type 1 error may be compared with a so-called false positive in tests where a single condition is tested for. The Type 1 error rate or significance level is the probability of rejecting the null hypothesis given that it is true. It is denoted by the Greek letter alpha and is also called the alpha level. Often, the significance level is set to 0.05, implying that it is acceptable to have a 5% probability of incorrectly rejecting the null hypothesis. Type 1 errors are philosophically a focus of skepticism and Occam's razor. A Type 1 error occurs when we believe a falsehood. In terms of folk tales, an investigator may be crying wolf without a wolf in sight. Type 2 error. A Type 2 error, also known as an error of the second kind, occurs when the null hypothesis is false, but erroneously fails to be rejected. It is failing to assert what is present, a myth. A Type 2 error is committed when we fail to believe a truth. In terms of folk tales, an investigator may fail to see the wolf. Again, H0, no wolf. The rate of the Type 2 error is denoted by the Greek letter beta and related to the power of a test. What we actually call Type 1 or Type 2 error depends directly on the null hypothesis. Negation of the null hypothesis causes Type 1 and Type 2 errors to switch roles. The goal of the test is to determine if the null hypothesis can be rejected. A statistical test can either reject or fail to reject a null hypothesis, but never prove it true. Table of error types. Tabularized relations between truth, falseness of the null hypothesis and outcomes of the test. Examples. Example 1. Hypothesis: adding water to toothpaste protects against cavities. Null hypothesis: adding water to toothpaste has no effect on cavities. This null hypothesis is tested against experimental data with a view to nullifying it with evidence to the contrary. A Type 1 occurs when detecting an effect that is not present. The null hypothesis is true, but this null hypothesis is rejected based on bad experimental data. Example 2. Hypothesis: adding fluoride to toothpaste protects against cavities. Null hypothesis: adding fluoride to toothpaste has no effect on cavities. This null hypothesis is tested against experimental data with a view to nullifying it with evidence to the contrary. A Type 2 error occurs when failing to detect an effect that is present. The null hypothesis is false, but the experimental data is such that the null hypothesis cannot be rejected. Example 3. Hypothesis: the evidence produced before the court proves that this man is guilty. Null hypothesis: this man is innocent. A Type 1 error occurs when convicting an innocent person. A Type 2 error occurs when letting a guilty person go free. A positive correct outcome occurs when convicting a guilty person. A negative correct outcome occurs when letting an innocent person go free. Example 4. Hypothesis: a patient's symptoms improve after treatment more rapidly than after a placebo treatment. Null hypothesis: A patient's symptoms after treatment are indistinguishable from a placebo. This kind of hypothesis error may happen due to staff failing to keep patients unaware of which treatment they're receiving, to uncontrolled variables, to difficulty tracking subjective symptoms like pain, or for many other reasons. A type 1 error would falsely indicate that treatment A is substantially more effective than the placebo, whereas in a type 2 error the mistake is believing that treatment A has no effect. Theory from the Bayesian point of view. A type 1 error is one that looks at information that should not substantially change one's prior estimate of probability, but does. A type 2 error is one that looks at information which should change one's estimate, but does not. Hypothesis testing is the art of testing whether a variation between two sample distributions can be explained by chance or not. In many practical applications, type 1 errors are more delicate than type 2 errors. In these cases, care is usually focused on minimizing the occurrence of this statistical error. Suppose the probability for a type 1 error is 1%, then there is a 1% chance that the observed variation is not true. This is called the level of significance, denoted with the Greek letter alpha. While 1% might be an acceptable level of significance for one application, a different application can require a very different level. For example, the standard goal of 6 sigma is to achieve precision to 4.5 standard deviations above or below the mean. This means that only 3.4 parts per million are allowed to be deficient in a normally distributed process. Etymology. In 1928, Jerzy Neyman and Egon Pearson, both eminent statisticians, discussed the problems associated with deciding whether or not a particular sample may be judged as likely to have been randomly drawn from a certain population, p1, and, as Florence Nightingale David remarked, it is necessary to remember the adjective random in the term random sample should apply to the method of drawing the sample and not to the sample itself. They identified two sources of error, namely, the error of rejecting a hypothesis that should have been accepted, and the error of accepting a hypothesis that should have been rejected, p. 31 in 1930. They elaborated on these two sources of error, remarking that, in testing hypotheses, two considerations must be kept in view. We must be able to reduce the chance of rejecting a true hypothesis to as low a value as desired. The test must be so devised that it will reject the hypothesis tested when it is likely to be false. In 1933, they observed that these problems are rarely presented in such a form that we can discriminate with certainty between the true and false hypothesis. They also noted that, in deciding whether to accept or reject a particular hypothesis amongst a set of alternative hypotheses, H1, H2, it was easy to make an error, and these errors will be of two kinds. We reject H0, i.e., the hypothesis to be tested, when it is true. We accept H0 when some alternative hypothesis H or H1 is true. p. 187. In all of the papers co-written by Neyman and Pearson, the expression H0 always signifies the hypothesis to be tested. In the same paper, 190, they call these two sources of error, errors of type 1 and errors of type 2 respectively. Related terms. Null hypothesis. It is standard practice for statisticians to conduct tests in order to determine whether or not a speculative hypothesis concerning the observed phenomena of the world can be supported. The results of such testing determine whether a particular set of results agrees reasonably with the speculated hypothesis, on the basis that it is always assumed, by statistical convention, that the speculated hypothesis is wrong, and the so-called null hypothesis, that the observed phenomena simply occur by chance. The test will determine whether this hypothesis is right or wrong. This is why the hypothesis under test is often called the null hypothesis, because it is this hypothesis that is to be either nullified or not nullified by the test. When the null hypothesis is nullified, it is possible to conclude that data support the alternative hypothesis. The consistent application by statisticians of Neyman and Pearson's convention of representing the hypothesis to be tested with the expression H0 has led to circumstances where many understand the term the null hypothesis as meaning the nil hypothesis, a statement that the results in question have arisen through chance. This is not necessarily the case. The key restriction, as per Fisher, is that the null hypothesis must be exact, that is free from vagueness and ambiguity, because it must supply the basis of the problem of distribution, of which the test of significance is the solution. As a consequence of this, in experimental science, the null hypothesis is generally a statement that a particular treatment has no effect. In observational science, it is that there is no difference between the value of a particular measured variable and that of an experimental prediction. Statistical significance: the extent to which the test in question shows that the speculated hypothesis has been nullified is called its significance level, and the higher the significance level, the less likely it is that the phenomena in question could have been produced by chance alone. British statistician Sir Ronald Aylmer Fisher stressed that the null hypothesis is never proved or established, but is possibly disproved, in the course of experimentation. Every experiment may be said to exist only in order to give the facts a chance of disproving the null hypothesis.